Okay, let's get started for today. Good to see you all. Showing again your persistence, neither hail nor ice nor snow can stop us. Couple quick announcements. I think most of you are aware that homework number 3 is due Wednesday. And I hear that all is going well. People are successfully being able to use the auto-grade system. So if you're having any difficulty with that, be sure to take a look at Piazza and the explanations there. We will hand out, the next assignment won't be out until next week. So homework number 4 will come out on Monday. We're going to do probably a total of roughly 7 homeworks. I told some of you 6 earlier in the semester, roughly 6. We decided to split some of the bigger ones into smaller ones. But as you'll notice from the arithmetic, that means most of the homework assignments will happen before the midterm. And then after the midterm, we'll reduce significantly the rate of homework assignments because we want you instead to be able to work on your projects. By the end of this week, we'll have a page up on our website describing the idea of the projects. And as you'll see, we're going to provide a number of data sets that you could choose one of those to work with. And if you want to bring your own data set, you could do that too, but you have to then write up a description of your project and assure us that you actually have the data already. You're encouraged to work with some other students. So we're thinking of teams of 2 and 3 people to do the projects. And like I say, we'll have more about that by the end of this week. There's a required reading for today, which is on our website. If you go to the lectures tab of the class website, you'll see this reading. You can download it. And also, as I said in my email yesterday, there's another reading which covers the material which we did last week, really, on maximum likelihood and map estimation. You're welcome to take a look at that. For both of these, if you find any ways to improve it, please let me know. I'm interested in refining this and making it more useful for other people in the future. Okay, any questions about logistics before we talk technical? Okay, let's get started then. So we were talking last time about Gaussian naive Bayes. And I mentioned earlier in the semester that I have a couple pictures I carry around in my head. And so I thought I would share one of the pictures for Gaussian naive Bayes. As we discussed, Gaussian naive Bayes is just like discrete valued naive Bayes, except that we assume the x sub i's are continuous variables. And so we have to have some kind of probability distribution that's appropriate for characterizing p of x sub I given y. And the reason we call it Gaussian naive Bayes is we choose a Gaussian distribution to do that. And so here's a, I think, helpful picture. Let's take a simple example of saying that we're trying to predict a Boolean variable, whether somebody plays basketball or not, based on 2 continuous variables, their height and their machine learning grade. And so because they're continuous variables, it's kind of handy to think of the 2-dimensional space in which they live. So let me call this one x1. That's height. So here would be the height of a person. And here's x2. We could call that the machine learning grade. And so we could plot any given person, any given example as a point in this 2-dimensional space. If we want to train our naive Bayes classifier, there are basically 2 kinds of probabilities that we need to learn from our training data. One are just the priors on the class y equals 1 and y equals 0. Let's assume in this example priors are 0.5. The other is the probability distribution on, well, each of our two variables, height and machine learning grade, conditioned on the value of y, whether you're a basketball player or not. So in this imaginary example, let's suppose that, in fact, it's more probable that you're a basketball player if you're tall than if you're short. And so I could draw, since I'm going to represent these distributions as Gaussians, let's suppose, just for the sake of the argument, that I have a Gaussian that looks kind of like this. For that'll be my Gaussian distribution. Let's say the probability on height equals, well, I'll just say x. I guess I could say x1. Given that y equals 1, and I'll have another Gaussian distribution, of course, for the other case where y equals 0. So this could be my probability distribution on height given that y equals 0, given that you're not a basketball player. Okay. So these will be the two distributions I'm going to have to learn from training data. And as we discussed last time, for each of those, I'll have some mean. To define a normal distribution, I need to have a mean. This will be the mean for x sub 1 and mu and y equals 0. Here's a different mean. This will be the mean for x sub 1 and y equals 1. Okay? And so given some training data, we might estimate these mu's and some sigma as well. We'll have a sigma here that characterizes the width of these distributions. One for the case where y equals 0, another distribution when y equals 1. Okay. And then similarly, of course, I'll have, for my other x sub I, x2, I'll have another pair of Gaussian distributions, one conditioned on the assumption that y equals 0, one for y equals 1. So I could draw those too. They might look like this. Which one should we make y equals 0? I think if you're a routine basketball player, you might not be studying quite as much. So this is the probability of your machine learning grade given that y equals 1, given that you are a basketball player. And probability of machine learning grade given that you're a total nerd. All right. Okay, so those are the distributions that we end up learning. These four conditional Gaussians conditioned on y equals 1 and 0 plus that prior up in the corner. Okay, so now here's my space of x's. I could plot any one of us somewhere on this two-dimensional plot. Where is, let me ask you a question. Where is the point, where's the combination of x1 and x2 which is most probable given that you are a basketball player? Right, so to be at the mean. So given that you are a basketball player, here's the probability of your height. Well, it looks like your most probable height is this. Similarly, your most probable machine learning grade is that. And so if we just connect those, I'm going to say around here, would be your most probable x, meaning x1 and x2. Your most probable x given that y equals 1. Where's the most probable x given that y equals 0? Because that now we'll choose this Gaussian. If y equals 0, we're going to draw an x according to this and that. And so the most probable point for y equals 0, most probable x, given that y equals 0, would be there. And since these are Gaussians, and we're assuming they're independent, right? X sub I are conditionally independent given y. That means I could just multiply any given probability here times any given probability here to get the probability of any x. That's what it means to be conditionally independent, right? So I could actually draw the topographic map of equal probabilities around each of these points. Whoa. So for example, there's actually a Gaussian distribution then here, which kind of looks like this. So here's the most probable x given that you're not a basketball player, and then the decreasing probability around there, which is simply the product of these two probability densities. And similarly for this one around y, so this is the one for y equals 0. I guess I should say p of x given y equals 0. And here for y equals 1, similarly. I'm going to draw this more carefully. Okay. So this is actually the way that I keep in mind what we're modeling when we train a Gaussian naive Bayes classifier, right? We're really just estimating these independently for each x sub I, the Gaussian distribution that goes with y equals 1 and y equals 0. And of course, we could have more than 2 values of y. For each value of y, we'll have another Gaussian. And then when we want to classify a point, what we're interested in is y, our new x, we want to assign the y new, which maximizes that quantity where the little y, the value, is either 0 or 1. We want to pick either 0 or 1 based on that. And so what we're going to do is multiply together each of these conditional probabilities under the assumption that y equals 1 and that y equals 0 and see which is greater and pick that one. So what would be the label of this point? Zero. That's a y equals 0 point. And I could, of course, I'll put a y hat there to mean it's our estimate. I could pick any point on that plane and ask for the label. So let me instead ask, where's the dividing surface, the decision surface here, between the region of the space where y equals 0 and where y equals 1? Right, so we're just going to have to find the place over here. P of x given y equals 1 is much higher than P of x given y equals 0. Here it's the other way around. We just need to find the surface where those two probability distributions collide, are equal, I should say. And here, so for example, if we believe this topo map that I drew, then here are 2 points, 1 point, where they're equal, right? 1, 2, 3, 4 rings out in each case, or 1, 2, 3 rings out in each case. And so there's actually a surface like this. And on this side, it's y equals 0. And on this side, it's y equals 1. Now I drew that as a straight line. Is it really a straight line?
Probably not.
In general, no. But if my Gaussians here are spherical, then in fact it will be. And in fact, the interesting thing we can say is that this will have a linear decision surface. If, well, here the answer is this, actually. If I think of each of these 4 Gaussians that I had to estimate during training as having a, let's say it goes with the ith variable and the kth y, then this is a linear decision surface if these 2 are the same for all k and j. So it turns out if the sigmas, if these variances are the same for independent of class, then it turns out that this will end up being a linear decision surface. And if they're not, then it usually won't be. And one way to, I could also, for example, instead of hanging with spherical Gaussian, I could have a Gaussian that looks like this. Colliding with a Gaussian that looks like this. And those won't necessarily have a linear decision surface between them. But it turns out that it will be linear if that's the case. And we'll see more about that soon. Yes?
What is the effect of the prior on the linear decision surface?
Oh, yeah, that's good. That's a great question. It turns out that this is true regardless of the prior. So even if the prior is not 0.5, if this holds, then it'll still be a linear decision surface. It's not intuitively obvious. You have to work out the arithmetic to see that. Yes?
So, the case that we have the linear decision surface, is it related to these 2 variables being independent?
It does. It's a consequence of the naive Bayes assumption that we're assuming P of x equals just the product of P of x1 and P of x2, x being the vector, x1 and x2. So it does follow from that independence assumption. Plus, to make it linear, we have to push in this additional assumption. Okay. But you can also see how if you had non-spherical Gaussians that had different, non-spherical means you're going to have a different sigma this direction than you have this direction. And if they were different also by class, then you could easily make nonlinear decision surfaces. Okay, but I think this picture is helpful to keep in mind because then you can, I don't know, it just helps me think about the different probability terms that we're estimating and what they really mean in terms of contributing toward the actual probability of the entire x, not just the component features x sub I. And the independence assumption is simply that for any point here, if we want to know the p of x given y equals 0, we multiply whatever we have for this y equals 0 for this term times the y equals 0 from that distribution, and that gives it. Okay, so I just wanted to share that with you. I find it helpful, thought you might. But the main topic for today is actually closely related to that big picture, is now that we're all experts at naive Bayes, the gnawing question that was probably keeping you awake at night, I hope, is, well, Tom, why are we bothering to learn, if what we're interested in is learning P of y given x, why are you having us instead learn P of y and P of x given y and make these ridiculous assumptions about conditional independence and then use those learned things to calculate from Bayes' rule P of y given x? Why don't we just learn P of y given x directly? And we kind of talked about that a little bit last time, because when we were talking about, the number of rows in the conditional distribution table that we would have to estimate would still be, if we had n Boolean features here, we'd still have 2 to the n rows if we wanted to estimate all the P of y for all the x's. But now that we've made the conditional independence assumption, now that we've agreed that's what we're going to do for naive Bayes, it's interesting to ask, well, if we only make that conditional independence assumption, what is the implied form of P of y given x? And then let's see what we can do with that. That leads to a really widely used algorithm called logistic regression. And we can actually derive the form of it just starting with the naive Bayes assumptions, and voila, we'll get logistic regression. So that's the plan for today. Okay, so let's look at that. So to be precise, I'm interested in learning some function from x to y, or equivalently, we're going to think of learning P of y given x. And I'm going to assume again that x is a vector of, let's say, real valued features, just like in Gaussian naive Bayes. Y is Boolean. All the x sub I are conditionally independent given y. And that we're going to model each P of xi given y as a Gaussian. And notice how I carefully chose sigma to be only dependent on which feature x sub I it is. And I did not choose the general form. I could choose, but that is estimating a different sigma for each x sub I and each value of y. The reason I did that is this is what's going to give us the logistic regression form, just like it's what gave us the linear decision surface in our big picture. And I'm going to model y as just a coin flip Bernoulli variable, 1, 0, with a single parameter, pi we'll call it. Same one as theta we called before, just giving us the priors. So then what does that, if we just plug this in, we get a P of y given x that we can calculate from Bayes' rule. If we do that, it gives us a particular form, parametric form for P of y given x. And here's the form. So if we make exactly those assumptions and no others, it follows that P of y given x is of this form, where these w's are different parameters, different weights, we'll call them. And the x sub i's are just the values of the different x sub I features. And this is the logistic regression form of, this is what we learn when we train a logistic regression function. And what we learn from the training data are estimates of these different w's. Okay, so why is that the case? Well, here's the derivation, and in the required reading, the derivation is there in full gory detail. Here I'm just going to sketch it, but it's pretty straightforward. So if I just write down the expression for the probability that y equals 1 given x, starting with Bayes' rule, then in the first step, all I'm doing is dividing by the numerator. So if I divide by the numerator, now the numerator becomes 1, and the denominator, this numerator is the same as this expression. These two things are the same. So I get a 1 plus the second term divided by the numerator. And then, for reasons that seem kind of silly, but will turn out to be fortunate for us, we appear to complicate the expression just by taking the exponent of the log. And that we can do that just because for any x, x equals the exponential of the log of x. That's kind of the definition of log, right? So all I'm doing here is taking what we already had and just saying, let me put an exponential and a log around that. The reason I'm doing that is now I can take the log of that product and turn it into the sum of their logs. So this log of p of y equals 0 over y equals 1 is now just the log. Oh, here I haven't actually changed anything. I'm just plugging in our estimates. Remember, we're defining pi as just defined to be the probability that y equals 1. But now I've separated out that ratio from this second ratio that depends on these. Okay, and none of that has anything to do with Gaussians. That's just simple facts that follow directly from Bayes' rule. At this point, if I want to expand this further, I can look into the fact that we're going to model these p of x sub I given y's as Gaussian distributions. Again, we are going to assume that sigma is independent of the value of y. And if we do that, and again, the details are in the required reading, but if we do that, then what we find is that each of these the log of each of these ratios for any given x sub I is just this quantity, where these are the means and the variances for the ith features for y equals 1 and y equals 0 for the mean. And you can work out this, and it's in the reading, as I mentioned. But the interesting thing here is now you can see that this turns into a linear sum of a bunch of constants that don't depend on x, and x times some coefficient. And so we can finally, if we carry that all the way through, we do see that just as promised, p of y given x is of this form. And in fact, we can even solve for what those w sub I weights are given this derivation. Okay? So what we've seen here, to summarize, is that if we just start with the same assumptions as Gaussian naive Bayes plus this little extra assumption, then p of y given x will always be of this form. And furthermore, these weights, we can derive their values in terms of the means and the variances of the different class-conditioned Gaussians. Okay, well, that's nice. Actually, the reason that we care about this is that this turns out to be a very convenient expression in a lot of ways. So let's see how. Whoops, I don't want to give away the answer. So there's our expression at the top again. So let me ask you, if that's what the expression is for p of y equals 1 given x, then what expression should I write down for p of y equals 0 given x? Yeah, it's 1 minus that. So I'll give you the denominator. You give me the numerator.
same expression as a denominator minus 1.
Right. It's just this. Right? And you can verify that they sum to 1. If you add them up, you get 1 plus x blah over 1 plus same thing. Okay. Then what's the ratio? If I want to take the ratio of y equals 0 to y equals probability of y equals 0 to 1 given an x, what's the ratio? Right. It's just this. I've got to either get a different arm or a different computer. Good. And this is kind of interesting because, as we talked about before, if this ratio is above 1, that's all we need to know in order to decide to label this y equals 0. If the ratio is below 1, we're going to label it y equals 1. So all we have to really do once we've trained our model is look at this expression and see whether it's above or below 1. Or equivalently, so we're interested in whether this quantity is more or less than 1. Equivalently, we could ask whether the log, of course, is more or less than 0. And the log of that is even easier. That's our linear decision surface. In fact, the idea of logistic regression is to just directly learn the coefficients that define the linear decision surface instead of going through all the rigmarole of learning the mu's and the sigmas and then solving for things afterward. But it's not just that we only know whether to say yes or no. We also know the probability of y given x because of these expressions. So we're not giving up anything. We can use this form if we just want to say whether y is more probably 1 or 0. But if we want to really know the probabilities, we have these also relatively simple expressions just to use to plug things into. Okay, so that's the idea of logistic regression. Instead of learning our mu's and sigmas, we're just going to learn the w's directly from the data. And this will have a couple of advantages. One is sometimes we will find that if we don't have infinite data, that's all the time. Sometimes we will find that we get more reliable estimates given limited data by estimating the w's directly instead of going through the intermediate step of getting the mu's and the sigmas. In addition, it will turn out that we're going to use a method for training these weights that even though this derivation that we did of the form, the parametric form of p of y given x, depended on the conditional independence assumption, the way in which we train logistic regression to pick the actual values that we're going to use as our estimates of these, that training method is freed from the conditional independence assumption. So in that sense, logistic regression is a little bit less handcuffed by the conditional independence assumption than the way in which we would train our mu's and sigmas. Even though it's partially handcuffed because, as you saw, when we derived this form for p of y given x, we were making the conditional independence assumption. Plus that other little annoying assumption about the sigmas being independent of y. Okay, so let's also take a look at what that logistic function looks like. This 1 over 1 plus exp of something is often called a sigmoid function. Here's what it looks like. I do 1 over 1 plus exponential of minus b. The value of that function ranges from 0 to 1. Well, that would have to be since it's giving us a probability. And here you can see that as b varies, that is, as this quantity varies, if its value is 0, we get an output of 0.5. So if this quantity is 0, we get an output of 0.5. And as it grows one direction or the other, we get closer and closer to 0 and 1. Okay. So far, we've derived this logistic regression expression, assuming that y is just a Boolean variable. In fact, we can do the same thing. It extends easily to the case where y is any discrete valued variable with any number of values. It's just that if y takes on, say, r values, then we have to learn for each of these possible values a separate set of weights. So now I have, for example, for y equals little yk, I have a weight that depends both on, for each feature I, each x sub I, and for each value of y sub k. And in fact, because these probabilities sum to 1, right? If I give you an x and I say there are 13 possible classes, and if you calculate the probability for 12 of those 13, you get the last one for free because those probabilities do have to sum for 1 to 1. And so we actually need r minus 1 sets of weights. And the last, of course, we can just take 1 minus that sum, which will give us this. And this is the same thing we saw when I asked you, what's the probability of y equals 0 given x? And you all said, oh, it's just 1 minus what we already had. Okay, so there's a simple extension of this to y takes on any number of discrete values. So that's logistic regression. So now let's talk about training it. I love this part of the course because now you can really see what the pattern is that we're falling into. We've set up everything now in the course. You're experts on maximum likelihood estimation. You're experts on map estimation. We have a new form, we want to train it. And I ask you, how can we derive an algorithm? You're going to shout back at me, well, let's use our maximum likelihood or our map estimation methods and derive the right training rule. You're right, let's do that. Okay, so now we can do this a little bit with a little bit more subtlety, because in logistic regression, let's look at the details here. We have a set of training data we want to train our logistic function from. That means we want to use this training data to estimate all those W parameters. Each training example is some x and the corresponding y. When I write x here, I mean the whole vector of all the x sub 1 through x sub n. And of course, for maximum likelihood estimate of those parameters, what I'd want is to pick the vector of W weights that make the data most probable given W, standard maximum likelihood estimate, which I could also write this way as the product over all the training examples of the probability of observing them given our parameters. But it turns out with logistic regression, we can make the problem somewhat easier by saying, well, we're never going to have to predict what the x's are. We're going to always be given an x. The only thing we're going to have to be able to predict is the y's. And so instead of maximizing the joint probability of x and y, given our weights, I can instead train the system to maximize the conditional likelihood, that is, the probability of just x given y. Oh, got it backwards, Tom. Somebody should have corrected me there. Okay, so instead of trying to pick the W that maximize the joint probability of x and y, given that we're always going to be shown the x, we don't really care what that probability is. All we need to do is maximize the conditional probability of y's, the training labels y, given the x's that we do observe. And so this is what we'll call this the conditional, or maybe maximum conditional likelihood. Maximum conditional likelihood estimate. Okay? It's the same principle, really. Before, when we were trying to justify maximum likelihood estimates, we said something like, well, clearly we want the parameters to make the observed data as probable as it can be. And here we're saying, yeah, but we don't have to bother with the x's. Those are shown to us. So let's just then make the y's as probable as they can be, given the corresponding x. Does that make sense? Good. So we can apply that maximum likelihood principle to any probability distribution. Could be a joint distribution, could be a conditional distribution. It's the same principle, it's just the form of the distribution we're applying it to. Okay, so now let's do that. I guess this is just summarizing what we said. So we're now going to choose our parameters, that vector of W weights, in a way that maximizes the conditional likelihood. Our data looks like this, but instead of maximizing the full likelihood, we'll just worry about the probability of the y's given the x's, and pick the W that maximizes that. Now, okay, so that's good. That's the principle. But just like when we were worrying about coin flips, once we wrote down the principle, we had to then derive a formula for what, given the x's and y's, in the case of the coins, given the x's, what would be the theta. Here we have to say, well, we need a formula so that given the x's and the y's, what will be the w's. And when we do that, to do that, we have to start by writing down an expression for the conditional likelihood itself. So again, the conditional likelihood is just the product over all the training examples. That's what L is. L is the ELF training example of observing the ELF, the label Y for the ELF example, given the X's for the ELF example. Again, it turns out to be more convenient to work with the log. So we can instead take the log of that probability and therefore the log of the conditional likelihood. If we write that down, one simple way to write it down is with this expression. Remember, this is kind of a arithmetic expression for an if statement, really. If y can only be 1 or 0, then this statement is saying, well, the likelihood, the log likelihood for the ELF example, if y equals 1, we're going to use this term. And if y equals 0, then this term will be 1, and we'll use this one. So we're either going to take, if y equals 1, the log probability that our weights have assigned to that, or if y equals 0, the log probability that they've assigned to y being 0. That's the conditional likelihood. Then we can rearrange that a little. This first step, all we're doing is taking the minus y times that, and noticing that we can merge that into here to take the y that would give us the log of this minus the log of that. But the log of something minus something is the same as the log of its ratio. And that leaves us the 1 times this, which we've still got here. And then finally, if we plug in our logistic function form with the x's and the w's, then as we already discussed, this is this beautiful linear form. We already talked about that. And here we get this expression. Okay, so now we have a formula for the log of the conditional likelihood given a set of weights, vector of weights, W0 through whatever. Here's the formula for the log of the conditional likelihood of all the labeled example y's given all of the training example x's. And so now all we have to do is find the w, the vector of weights that maximizes the conditional likelihood, maximizes this expression. Okay, so good news and bad news about this. The good news is this is, in fact, a concave function of the weights. If it's a concave function, that's good because it means we have a chance of running various optimization algorithms to find the optimum value. But the bad news is it's not a concave function with a closed form solution. Okay. So this gives us a chance to illustrate 2 general points about machine learning. We're at this point where we know what we want to optimize. We're going to follow the maximum likelihood principle, in this case maximum conditional likelihood. And we've managed to turn the question of how do we design a learning algorithm into the equivalent question in this case of how do we solve for the optimal set of w's that will maximize this expression. We do that a lot, it turns out. Many of the algorithms that we talk about in machine learning, in the end, turn out to be optimization algorithms. Basically, what we have on our hands here is an optimization problem. Here's an objective we're trying to maximize, and we just need to find the w's that'll give us the greatest value for that. So we have an objective function and a standard optimization problem. Yes?
So the way you describe now the algorithm is an objective over the sample, right?
This is an objective over the sample.
True objective that is underlined.
Ah, great question. This objective function is defined over the sample of training data. That was the comment, which is absolutely correct, right? This is the ELF training example. So we have some world we're trying to model, like maybe the world where we're trying to predict who plays basketball and who doesn't based on their grades and their height. But we only have a sample of some people, like maybe these people, to be our training set. And of course, the objective we really want is the classifier or the predictor that will work best on the real universe of people. And why don't we just do that? Because we don't have the real universe of people at hand. All we have is this sample of training data, so we're stuck. The only thing we can do really is design an algorithm that uses the available information, which is this sample. So we hope that the sample is representative of the true universe. And to the degree that it is, then this is a good thing to be doing. And we will be talking a little bit later about what kind of trouble we can get in and whether we can bound the trouble that we get in by taking samples of different size in different ways from that universe that's out there. So it's a good reminder, though, that we're really still defining that objective function in a way that we're forced into, that it's in terms of the training data. Okay, so the final principle this illustrates is that even though there are a lot of algorithms for doing optimization, for solving optimization problems. And you can take courses in optimization. In fact, the machine learning department offers a fantastic course in optimization methods. The good news is there's a fallback position that is widely used called gradient ascent or gradient descent, depending on whether you're trying to maximize or minimize your objective. And in fact, gradient ascent is arguably the best way to solve logistic regression. So we're going to we're going to go through gradient ascent for this. We'll derive it. And you'll see all the way down how to implement your own logistic function. But equally importantly, you'll see, oh, this gradient method just would work for even other kinds of concave functions that we're trying to optimize. So let's take a look at gradient. Oops, I have gradient descent instead of ascent. It's okay. So suppose we're trying to minimize some objective. And let's call that objective the function e. So I have some function, So I have some function e of my weight vector. And I just want to pick the weights, the vector of weights that'll minimize e. So what I've done here is I've just drawn a plot. This is weight 1. This is weight 2. Let's say weight 0. And this is E. Okay, so you can imagine that for any, in this simple case, I just have 2 weights. For any pair of weights I choose, that's some point on this plane. And for that particular point on the plane, there will be some corresponding value of E. And so I can define this whole surface, the value of the function E, for any given point on the W0, W1 plane. The idea of gradient descent is, how many people here already know gradient descent? Okay, some, not all. So the idea is fortunately very simple. If I asked you, how do you think, if I start with a random choice of W0 and W1, like that red dot there, and I ask you, which direction should I move W0 and W1 to make it better, that is, to make the value of the function closer to its minimum, then you'd probably say, move downhill, not uphill. I'd be with you. And that's the idea of gradient descent. And it's called gradient descent simply because the gradient is the mathematical formula for what it means to go downhill in the steepest direction. So the gradient formally is a vector of derivatives. So as you can see, in our case, E depends on both W0 and W1. So in this case, the gradient would be just the vector of these 2 derivatives. Wouldn't have more than these 2. It's the derivative of E with respect to W0. And I drew these as partial derivatives because you can see the derivative, which is just the slope of that curve, varies as we move around W0 and W1. Like where the red dot is, the gradient is pushing this way. The slope is this way, whereas if I picked a W over here, it would be a different value. So the gradient of W for a given weight is just the vector of partial derivatives. So in our case, for example, just these 2. And then the algorithm or the rule for gradient descent is that we just pick a random W0, W1 to begin with, like that red one. We calculate the gradient, that is the derivatives of E at that particular point with respect to the 2 weights. We move in that direction, which will be downhill. And when we move in that direction, what I mean is we update our vector to be the vector, in this case minus, because we want to go downhill, the gradient. So we just update weight to be that. And I could even say this is the I plus 1th estimate, and this is the ith estimate of W. We're just going to repeat this process. Did I get uphill, downhill, the right direction? Yeah, I did. Okay. So, in other words, we'll change, once we get the gradient, that actually tells us the direction to move W. That's what the gradient is. So the gradient actually it's a vector which is in the same dimension as the W0, W1 space. And when we add that vector to the vector that, or subtract that vector from the vector we already have, I see the gradient is pointing uphill, which is why subtracting it is better than adding it. So the gradient is pointing uphill. If we just use that vector directly in the W0, W1 space and subtract it, it moves W in the right direction. And now we iterate, because now we have a new set of weights. We can project that onto E here again and just repeat. And so we repeat, and we end up crawling down this surface into the hole, into the well. And there's some little details about how big a step to take. And often in gradient descent, what we do is we start with a step of some reasonable size, and then as the process continues, sometimes we shrink that step size. And you can see the problem with the step size being too big is that if I have some well that looks like this, and I'm starting here and I'm coming down with this kind of step size, when I get down to the bottom, if I take too big a step, I actually miss the bottom. Of course, then I'll come back on my next gradient descent, but I could bounce back and forth for a long time. And if I instead shrink the size of the update step as the number of iterations grows, then I'll get closer and closer down into the true bottom. Okay, so as you can see, this idea of gradient descent is very generic. Anytime we have an objective we're trying to minimize, we can use gradient descent. Or if we just stand on our heads, use gradient ascent to maximize something like the conditional likelihood. Okay, so let's see. There's one subtlety I also want to mention. This really is a technical point about gradient descent, but it's a really valuable technical point if you have a large data set. What I just described is called batch gradient, where the idea is we're going to, if we have some function E which we're trying to minimize, then we're going to compute the gradient, update our vector of weights with that gradient until it's, in that case, minimized. You could make the corresponding argument for maximized. An even more efficient algorithm for accomplishing the same thing in many cases, you'll see which cases, it'll be obvious, is to use what we call stochastic gradient descent, where, let's suppose for the sake of argument, I have 1 million training examples. So batch gradient says, calculate, if we're like trying to maximize the conditional likelihood of those 1 million training examples given W, we're going to sum up over all 1 million examples the log of their conditional probability, get the gradient, solve for it, take a step, and repeat. And notice there's sum over 1 million examples each time I go through that step. The idea of stochastic gradient is that instead we just randomly pick one of those million examples with replacement. And then every time, well, we don't really calculate the gradient with respect to the whole set, but with a randomly chosen example. And we update the same way. But the interesting thing is, here I've used this symbol eta as the step size. Remember we talked about you need to choose the step size. Maybe you want to shrink that as you get close to the bottom. You can show that as that step size goes to 0, this algorithm becomes that algorithm. Under certain, if the gradient is relatively smooth, you can kind of see that if this step size is very small, after you take a little step, the gradient's going to be about the same as it was before you took the step. And so as this goes to 0, this algorithm becomes that algorithm. And it's particularly valuable when our data is very large. If we have 1 million examples, we can either sum over all million and get the true gradient and use it, or we can run 1 million times faster and just pick one example and take a step. So here we're really getting an approximation to the true gradient really quickly, as opposed to the correct gradient really slow. And often the trade-off is in favor of doing this. And you can imagine all kinds of more sophisticated strategies, like do this for a while, and then when you get close to the solution, switch to that. Or instead of sampling just one example, pick 3 and take the gradient over those 3. So you can imagine a lot of engineering things you could do that are intermediate between these two extremes. And we do in practice this, but I wanted to point this out because it's actually a very widely used method for more efficiently solving gradient ascent problems. Okay, so back to our main storyline then. Well, what's the gradient of our log likelihood? We had said before that we now had an expression for the log likelihood. In the required reading, you'll see that the gradient is indeed this quantity. Okay, so let's look at this quantity. This is saying the partial derivative of that conditional log likelihood, which we're trying to optimize, with respect to any given weight wi, which goes with feature xi in our logistic function, is just the sum over all the training examples, if we're doing batch gradient, of this quantity. And what is this quantity? It's the actual feature value of x sub I. How high, how tall are you really? Or what is your machine learning grade? Times the correct label, yes or no, you play basketball, minus the probability that our model, our current, given a current weights, the probability it would assign to the label being 1. That's pretty interesting. This quantity in the bracket is just how wrong is our estimate, right? Y could be 0 or 1. If y equals 1, we want the probability that it assigns to y being 1 to be high, to be 1. So if the label is 1 and our model using the current weights thinks it's 1, then then the gradient is 0. There's nothing to change. It's already assigned a probability of 1 to y equals 1. On the other hand, if y equals 0, what do we want the probability that we want to predict for y equals 1? Well, if y equals 0, we want this to be 0. We want the probability of y being 0 to be 1. Therefore, we want the probability of y being 1 to be 0. So you can see this is really, this quantity in the bracket, very intuitive. It's the misassigned probability mass being assigned by our current set of weights. And if they correctly, for every time y equals 1, assign a probability of y equals 1 of 1, then there's no misassigned probability mass. If they only say, oh, 0.8 y equals 1, then there's 0.2 misassigned probability mass. And so you can see what this gradient is doing is it's basically intuitively doing just the right thing. The further our assigned probability is from the truth, the more we ought to change, the bigger the derivative of our objective with respect to a small change in the weight. Okay, and again, the reading has the full derivation of this. It's not a hard derivation. Yes?
Can I ask you some big picture question? So why should we go from naive Bayes to this logistic regression? It seems like lots of hard work for the same purpose.
Yeah, that's good. Great question. So the question is, wait a minute, we're down in the details, but you haven't really convinced me, you haven't really convinced us, I think was the intention, that logistic regression is a better idea than naive Bayes. Because we know it's really fast to train naive Bayes. And now we have to go through this complicated stuff for logistic regression. The short answer is almost always this gives you better accuracy classifying. The longer answer is why would that be? And I'm trying to decide when to answer that question. Let me come back to this question. It is the right question, but I just want to get through just a couple more details of this and we'll wrap it up and we'll come back to that. So hold that thought. I just want to wrap this up because given that this is the derivative of the log likelihood with respect to the weight, here is, in fact, the logistic regression training algorithm. What you do is you start with if you like, randomly assigned weights. I usually start with weights of 0. And then you just iteratively update the weights. Each time you go through every weight, and the ith weight you update according to the following formula. And for the weight that's 0, there's a different formula which is in the reading. It's actually just substitute x equals 1, and you get it. So in terms of coding, this is a fairly straightforward thing to code, although it is true that in terms of execution time, this is a lot slower than simply calculating means and variances. Okay. All right, so now let's take on this question. I want to push 5 more minutes on the question. Because I want to finish the last point, which is, again, on this theme of every time we ask how can we train an algorithm, you should immediately say, well, what would be the maximum likelihood estimate approach? And you should say, what would be the map estimate approach? What we just went through was the maximum conditional likelihood. But remember, the map estimate involves not just making the data most probable by choosing our parameters, but actually making the parameters most probable given the data, plus some prior distribution that we had to make up on our parameters. So it turns out in almost every case where you have lots of features, people use map estimates instead of likelihood, maximizing likelihood, for logistic regression. And the idea is straightforward. What we do is, now instead of just maximizing the conditional likelihood like we did before, we want that times the prior. Because this is the numerator of Bayes' rule, which would maximize the probability of W given the data. And the most common thing is to assume a Gaussian prior on each weight, where the Gaussian has a 0 mean, which means we just assume weights are small, is all this prior really means. It means it's most probable that the weight will be 0, and then there's the smaller prior probability that the weight will be non-zero, equally negative or positive. But the bigger the weight, the less probable a priori. It's like saying most features are not relevant to predicting most things. If we put that in, it just gives us a tiny modification. Here was our map conditional maximum likelihood estimate rule for training logistic regression. And if instead we add in this prior as a zero mean Gaussian, it just gives us this additional term in the update. What is this term doing? Every time it's pushing W towards 0. So we're going to add to W everything we were adding before, plus this additional term. If W is positive, then this expression will be negative. If W is negative, this expression will be positive. Both ways it's pushing it towards 0. And again, this is just the step size for the gradient. And this lambda is a constant that we have to make up to say how much we're forcing these weights towards 0. That lambda is the same choice as saying what's the sigma in this Gaussian prior that we put on W. So if we use a wide sigma, that means, well, we're not really too certain that the weight should be 0. Or if we use a very tight sigma, a very small sigma, with a very peaked Gaussian, then we put a lot of strength on that. So this gamma is essentially a reflection of that sigma. And again, you can sit down at your leisure, plug in the Gaussian prior, and work through what the map estimate would be. But I think you see the intuition. OK. So questions there? Then we'll come back to this overarching question about why are we doing this at all. OK, so we went through a bunch of derivations here. That's why I really want you to read that required reading. It goes through them. You can kind of study them, and any that you're surprised about, that should clear it up. So let's move on then to this very interesting question of, well, what is the trade-off then between Gaussian naive Bayes or other kinds of naive Bayes and logistic regression? And oh, by the way, you can use this whether x is continuous or discrete. X could be Boolean, and this is still the, oh, we didn't show that. It turns out that if x is Boolean, you still get the same parametric form of p of y given x, the same one that we derived starting with Gaussian naive Bayes. So this logistic regression thing is more general. You can use it with combinations of continuous and discrete variables. But the question you're asking, which I think is just the right one, is, well, then what's the trade-off? We now have two different algorithms. They're closely related. We derived the parametric form of p of y given x because we liked naive Bayes. And now you're telling us here's a different strategy for estimating these weights directly. What's the trade-off? So intuitively, well, let me ask you, who has an answer or a route toward an answer?
Well, I think it's going to depend like what we value more. Do we value like the precision of our predictions, or we value like the efficiency?
That's good. So one comment, the comment down here was maybe there's a trade-off of efficiency of training for precision of accuracy of the trained model. And in fact, there is, but why would that even be? I mean, I said, and I was telling the truth, I would always go with logistic regression, almost always. Actually, I can show you. We will show you next time some cases where you should go one way or the other. But in most cases where I have a lot of data and a lot of features, I will go with logistic regression. And the reason is that empirically this just empirically it just almost always is the best choice, although not 100% of the time. But one way we can think about it is, what are the assumptions that are actually baked into these two algorithms? And is one more restrictive than the other? That is, how biased are these two algorithms? The other question we can ask is, given that we only have finite training data, is it true that one of these algorithms can converge toward its best parameter estimates using less data than the other? And it turns out these algorithms differ along both of those dimensions, which makes it pretty interesting. So let's start just by asking, well, how many different parameters are there being estimated in these two cases? And what are the assumptions baked into the learning algorithm? So let me ask you first, how many parameters, I'll just ask you here, how many parameters for Gaussian naive Bayes, and suppose we're learning a Boolean, we're trying to predict a Boolean y from a bunch of Boolean x's. Then the number of parameters we need, for a number of continuous, these are real valued x's. Then how many parameters do I need for Gaussian naive Bayes? How many am I estimating? 2n plus 1. Right. We talked about. No. The x's here are continuous, so we need a Gaussian per xi. And a Gaussian costs us two parameters, the mean and the sigma. Right, so 4n plus 1. And then remember we made that annoying little assumption that the sigmas, they depend on which x sub I we're looking at, but they don't depend on the y. So if we make that annoying assumption, if we assume sigma ik equals sigma I, then it's really just 3n. Is that right? Yeah. Right, because now we need a mu for y equals 1, a mu for y equals 0, and a sigma for each x sub I. Okay, now what about logistic regression? How many parameters? Wow. How quickly we forget the form of logistic regression. There it is. How many parameters to represent that probability distribution? N plus 1. Yeah, it's just the number of w's. Right, we have a w for each x sub I, plus we have a w0. N plus 1 parameters. Okay, so based on this, and that'll have to be all we base it on for today, but we'll come back to this question right away next time. Based on this, at least we can see that logistic regression involves estimating fewer parameters than naive Bayes. And all other things being equal, usually having fewer parameters means that we can get away with less training data to estimate them. But it also usually means that we have a more biased learner, because given fewer parameters, it's not as expressive. In this case, as we'll see next time, the trade-off is a little more subtle than that. it is true that logistic regression is both more biased and less biased than Gaussian naive Bayes. More biased in the sense that it only has n parameters. It can only represent linear decision surfaces. If we use this form of naive Bayes, then that's equivalent. But if we use the more open-ended form of naive Bayes where we can estimate different sigmas, then actually Gaussian naive Bayes in that case can get nonlinear decision surfaces. And so in that sense, logistic regression is more restricted. We can only do linear decision surfaces. However, it's less restricted in the following sense. When we train logistic regression with this gradient descent rule, there's nothing at all in that gradient descent rule that forces us to obey any conditional independence assumption. And therefore, logistic regression can learn linear decision surfaces that are very different from the ones that Gaussian naive Bayes will learn given the same data. Because it's optimizing a different objective. It's maximizing the conditional likelihood or that with a prior. Whereas naive Bayes is getting optimal maximum likelihood estimates of the mean and of the variance of each of these parameters. So they're actually optimizing different objectives, and for that reason, the comparison of the two is more subtle.
So the search space here for logistic regression is higher.
Say that?
The search space for logistic regression is higher, right?
Yeah, that's right. So the search space for logistic regression is actually larger, even though, and so that's the sense in which they both kind of dominate each other. Logistic regression, only linear decision surfaces, but more of them than Gaussian naive Bayes is going to learn. And then Gaussian naive Bayes could go nonlinear too if we allow the open-ended version. Okay, next time and feel free to read ahead and steal a look at the slides. Next time we'll actually cover a paper that was written specifically to address the question of what is the difference between logistic regression and Gaussian naive Bayes.